All right, guys, we're going to go ahead and start this lecture. So for this lecture, this is quality control. A lot of the portions of this lecture are things that we will have to know just flat out, unfortunately. There's not really many concepts in this unit. All of it is memorization. So, various people learn differently. You may need to make flashcards or Quizlets or things like that to get this information nailed down. This is information that's easily testable on the registry exam. And so we want to make sure we have it hammered down. That way we can get these questions right because they're just purely memorization. But when we talk about quality control, what we're talking about is a system where we are looking at our equipment, right? We want to make sure that our equipment is up to standard, that it's safe and that it's reliable to operate. Because if you think about it, we're using this on patients, right? And so if we're going to use it on patients, we need to make sure it's safe. And so quality control programs in that regard are required by the Joint Commission. The Joint Commission who comes and surveys hospitals, make sure they're operating properly. The Joint Commission actually requires quality control programs to be part of a radiography area. And so the quality control portion is the responsibility of everyone, okay? It's the responsibility of the radiologists, the managers, the physicists, quality control technologists, and even us as the general technologist. Quality control helps the department save money, right? Because if we establish something's wrong early, it may be easier to fix than when it starts becoming more of a problem, all right? And so there's many different parts and tests that we're going to see here. Now, quality assurance, quality control, that's a big difference that we're seeing. Quality control actually is going to deal with just the equipment. Okay, so we're looking at just the equipment, and that's why we're tested on it. Quality assurance is more of a idea or concept that every part of our department is going to relate to quality. And so that's customer service, that, they first meet the patient access person. When they get into the room, when they meet you, that customer service is part of quality assurance. Image interpretation by the radiologist, that's part of quality assurance. The accuracy of when they are diagnosing those images is part of quality assurance. And getting that report to where it needs to go is part of quality assurance. And so quality assurance is a more overarching part of a program. And then the last thing we have on this slide is continuous quality improvement. The way I would term it is nothing is good enough, right? We're going to always try to improve so that the processes are better. A lot of times places and departments and people get complacent, right? Once you're set in your ways, you really want to just do it the same way all the time. It's easier. But sometimes that's not something we can do, especially when we're dealing with people, right? We're making sure people are taken care of. And so we should always be constantly improving our processes to make everything better. And so that's what the focus of CQI is, or continuous quality improvement, is. We're always going to test our processes to make sure they're the best processes possible. And if we start to see slippage, hey, let's think about something that we can do to address that. Now, so for this PowerPoint, we're talking about quality control. There's 3 types of quality control tests that can be done: acceptance tests, routine maintenance, and error maintenance. Acceptance testing is that test that gets done right as something is newly installed, or if it gets majorly repaired. This acceptance testing is basically a testing done to say, hey, this is the amount that it needs to be outputting, and it's outputting that part. We accept the repair, or we accept that piece of equipment. And so that can be done by a technologist, physicist, service personnel employed by the hospital. It's used to determine whether the equipment is performing within what the vendor tells us. Now, routine maintenance has another name. You may have heard of it as preventative maintenance or PMs, right? The room 2 is going to go down today because they're going to do a PM on room 2, right? And so that's routine maintenance. We are going to perform preventative things to ensure that this piece of equipment will continue to work properly. Okay. And so usually during a PM or routine maintenance, they're going to check various things to ensure that they can catch a problem before it becomes apparent on an X-ray. That can be done by a technologist, physicist, or service personnel employed by the vendor. Now, error maintenance is when errors occur in the equipment's performance and that are so bad that corrective action must occur. And so when we talk about that, errors have happened, I'm sure, in your practice where, oh man, there's something appearing on this X-ray. I don't know what's happening. Or, hey, this machine is not connecting the detector to our packs, right? And so sometimes those error maintenance has to occur where we call the vendor. Only somebody from the vendor can come and fix that piece of equipment. All right. Because while it's operating with an error, that's going to give us poor performance with the equipment, number one, and then probably poor outcomes because we're not getting the images that we need. And so recognition and reporting of malfunctions. When we talk about this, understand that we as the technologist may be the first line in recognizing a malfunction. Why? We use the equipment on a day-to-day basis. We are the people who are using the equipment all the time. The physicist is not coming every day to test this piece of equipment. So it's important that we can recognize when something is not reporting how it's supposed to. It's very important. So that's why you should know how your equipment is operating, because we don't want to use that malfunctioning equipment on our patients. Okay. You never want to use anything that's not working properly on somebody that's trying to get an exam. So now here is these portions, guys, that are strictly memorization. What I tried to do was I tried to highlight all the important parts. I would definitely know all the highlighted parts. Okay, this is stuff that's going to be tested on the final. This is what's going to be tested on the quiz, and things like that. But half value layers measured, we're going to measure the filtration. Essentially, what it needs to measure is at 70 kV, that 2.5 millimeters of aluminum equivalent will cause the beam to reduce to half, essentially. With beam restriction, there's several ways we can check this. And one of the first things we check is light field to radiation field alignment. So when you guys turn that collimator light on, that is a guideline. It's not really the actual radiation field size, right? And so it can go out of alignment. And so we have to test it, right? And so with the light field to radiation field alignment, it must be accurate to plus or minus 2% of the SID. And so essentially, another thing we can test here is positive beam limitation, meaning when you place a cassette into the Bucky system, that it'll only open to the cassette size, right? But for the light field test, you can see here, they're using what's called a 9-penny test. So the pennies, you're going to place 2 pennies next to each other, and you're going to place 1 collimated edge in between the pennies, and you're going to do that for all 4 collimated edges. And then you're going to take the X-ray. And then when you take the x-ray, you can tell if it's in alignment or not. When you look at this x-ray here, you can see it. It's not in alignment because we thought here, the light field showed us that it ended here, but it went further than that. Okay. That's what's happening there. And so you use a collimator tool or the 9-penny test to assess that field size to radiation field. Central ray. It's important that our central ray is accurate, right? Because we're centering everything where our central ray is saying it is. And so the central ray actually needs to be plus or minus 1% of the light field's central ray. So whatever the central ray is showcasing, it should be really close to that point. If it's not, you'll see something like this. Look how not in alignment this is. Here, it's pretty much in alignment. This is a beam alignment tool that's being placed, and then they're taking the exposure so they can see whether or not it is in alignment. The effective focal spot. So we test the focal spot, all right? Because the focal spot can, the size of it can actually increase with age and use. So focal spot blooming is a thing. That's what it's called. So the focal spot we're measuring against what the manufacturer tells us it is. So the focal spot is plus or minus 50% of what the equipment specifications from the vendors told us. How we test it, probably should highlight this for this one. Star test pattern, pinhole camera, or slit camera is used. And there's various diagrams of those here, okay? And so that's how it's tested. KVP settings can drift over time. So with KVP accuracy, it should be plus or minus 3 to 5 kV on the control panel or plus or minus 10% of the KVP indicated. How we can test it, a computerized dosimeter is the most likely thing that we see. This is one of those computerized dosimeter things. The Wisconsin test cassette was something used previously, but you know, as we've moved to a digital environment, more things have gotten computerized. The timer. So the timer, this has two settings. One that's for exposures longer than 10 milliseconds, which is plus or minus 5%, or plus or minus 20% for exposures less than 10 milliseconds. All right. And so you use a digital X-ray timer that you're seeing here or a spinning top test. With MA, there's 3 tests that are taken. Linearity, reproducibility, and reciprocity. So linearity is saying we're going to take an X-ray at 80, 90, 100 MA. The value should increase by a set standard. It shouldn't be fluctuating all over the place. Those values should be within plus or minus 10% of what we expect. Reproducibility, this is the easy one. You're going to take the same exposure multiple times and then record the output. So it's similar to taking 3 X-rays at 100 MAS. The value should be roughly the same, plus or minus 5% of each other when you measure the amount of radiation output. Reciprocity. This one's tricky. Basically what it is you take 3 X-rays at the same value, so 100 MAS, but you're going to change the MA and time values to say 20 at 5 and 25 at 4 and 100 at 10. And those values will be recorded, and you should be within plus or minus 10% of those numbers as well. And a computerized dosimeter is used here for these. Now with automatic exposure control, the ion chambers that we use that pick up the radiation and tell us when to shut off the imaging should be plus or minus 10%. Density adjustment, that just depends on the manufacturer. There's not a set standard for that. Response capabilities. So minimum response time should be within plus or minus 10% of what we expect it to be. And then backup timer verification is just going to be verifying if the backup timer turns on after a prolonged exposure. So it's easy to verify the backup timer. Place a lead apron on a photocell that's being active, and then wait till it times out, essentially. You want to make sure that process works because we don't want that piece of equipment just to keep exposing patients forever. We need that backup timer to be working. In fluoro, you're probably going to go over this more in the fluoroscopy class itself. What we're seeing is it should not be more than 100 milligray air per minute or 10 Rankine per minute. All right. The automatic brightness control is also measured. It's used to check if the radiation dose is hitting the input phosphor properly. How you do that, you use a phantom and then measure if the dose is adjusted when you change the phantom's thickness. And so essentially what that would be is like you take a 5 centimeter thick block, you place it where the fluoroscopy table is, and then you place another 5 centimeter block and see if the automatic brightness control kicks in. One of the things that's different about fluoro has to be measured every 6 months. All the rest of the testing that we have up until this point was annually, but with fluoro, it is every 6 months. Now, as part of the quality control things that we do, there's a variety of different things that have to be complete. Plate reader erasure. So if you're working in a place with CR, you want to make sure this is being done weekly, right? Because if you can see here, there's a ghost image of a pelvis. If you look really, really hard, you can see the obturator foramen right here, right? You see the wing of an ala here. You can see another wing here, right? You can see the pelvis, the inlet right here, right? And so if the plate reader is not erasing properly, you're going to get those. So we want to make sure we're testing the plate reader weekly. Plate uniformity, this is annually. This is going to be measuring the software to see if there's any degradation of the uniformity. And so what we do is we take an x-ray and then we place 5 ROIs across the entire detector. And then we see if there's any differences between the areas. There should be less than 20 value differences between the numbers. Notice here, there's a lot more value difference from here to here. That's why you can see on the cassette, it's more lighter here than it is over here. When all the shades are similar, it looks like a similar uniform background. When we talk about spatial resolution, this also has to get tested every 6 months. It's measured in line pairs per millimeter. Essentially, the digital imaging systems must have at least 2.5 millimeters of line, 2.5 line pairs per millimeter of spatial resolution. If not, you're going to probably have to call a service engineer out. Detector calibrations. I know when I was working, I had to do this like every day. Some places do it weekly, but essentially you calibrate the detector to ensure it's working properly. Okay, there's a flat field and a dark noise test that gets performed. Plate reader calibrations. So the plate reader, we want to make sure it's operating within normal limits. Like I said before, you want to make sure it's connecting to the workstation if you're working with those CR plates. The grayscale standard display function. So this is something that deals with our monitors, okay? And so the American Association of Physicists in Medicine said that the grayscale standard display function cannot vary more than 10%. Again, guys, like I said, there's not really anything I can do to help you remember this other than say this is a remembering point. A lot of these values are because in practice, most of us are not measuring this. This is measured by somebody else, probably a quality control tech, a lead tech, somebody like that. But monitors have to be measured and they should not vary more than 10%. Here's some of the things that monitors are tested with. You know, there's these monitor test patterns that are put up. You're supposed to be able to see these dots on your monitor, right? There's a box within a box here. You're supposed to see those to ensure your monitor has the adequate amount of resolution. Another one here, right? You're supposed to be able to identify certain areas. So primary monitors have average luminescence between 300 to 500 candela per meter squared. When we measure the maximum to minimum luminescence or the output of light It's recommended to be at least 250 at the maximum, 100 at the minimum. We talk about shielding accessories. These should be checked every 6 months visually, okay? But every year, shielding accessories need to be checked at least once a year under X-ray or under fluoroscopy so that we can check it for cracking, like you see here. That's governed by a lot of requirements. The state, federal, Joint Commission all have requirements on monitoring lead shield accessories. And the last thing we're going to talk about today, guys, is going to be this aspect here, okay? This aspect here is image identification. For a image to be legal, it has to have a side marker, so a left or right marker, and the patient ID somewhere on a patient ID and date somewhere on that film. If these two things are not on your piece of film, you have to repeat the image, or you should repeat the image to keep yourself legal. All right. As we know, there's two ways to mark an image. You can do it radiographically, or you can do it after the fact with an electronic marker. You should get in a habit of placing these markers radiographically. All right. The reason being, there's a lot of legal implications when you do not place a lead marker. There are a lot of things that can go wrong. And in your practice standards, we are placing lead markers, meaning the ASRT says that, we are placing these lead markers as part of our practice standards. So if you place a digital marker and then go chop off somebody's hand, right, or amputate a wrong leg, who's liable, right, if you put an electric marker on? Okay, so if you put a lead marker, it can only be changed at that point in time, and so that makes it more legal. And so that's what we're looking at with lead markers. Is very important. We have clinic here at one of our major children's hospitals, and what we see is the technologist will repeat images on kids if they don't have a marker on. And you think that's counterproductive, but when you think about when these people are dealing with x-rays, they're dealing with people and children who are in child abuse cases. And so every single image is going to be taken to a lawyer and a legal team. And so they have to have this on there. Okay. There are specialized markers we see here. You can have like weight bearing, flexion, extension, standing, all those jazz markers that, tell position or time, things like that. Nowadays, most of the ID and dates are digitally placed, right? We're not putting a blocker. Like when I was in school, you had to be mindful of the blocker, because when you put an x-ray in, there's going to be an area where we would put this information, the time, date, all this stuff. Nowadays it's on packs, right? And so you want to make sure the correct patient information and dates are selected when you're doing exams. That way they transfer over and they are properly put into the system. All right, guys, other than that, that is the end of our lecture. I took a screenshot of the participant list, so all 22 of you will be getting credit for this. Other than that, guys, take care. Keep on track with all the things that you guys are doing. We're grading those things as we speak. But in any case, I will see y'all next week. Actually, I won't see y'all next week. Let me put that into play. I'm gonna have a recording. I'm actually out of town next week for our lecture, so there'll be a recording. You won't have to write a summary or anything like that, but know that the recording is used for both the assignment and the quiz for next week. So please be sure you are doing that. I'll touch base with y'all after I get back from vacation. But other than that, guys, take care. I will see you when I see you. Bye.